My name is Tom McCuch. We're going to be talking about messaging for modern applications today. And the theme of this presentation is oriented around incremental adoption of messaging within your cloud application, so that that incremental adoption can be controlled and that the next step shouldn't be scary. My name's, as I said, Tom McCuch. I'm a staff systems engineer with VMware. I actually came to VMware with the SpringSource acquisition 2.5 years ago. Before that, I did a number of message-oriented middleware projects, primarily within the telco space, as a consultant and a product engineer. Today's agenda will be focused on modern applications, some trends that have an impact on messaging and application architecture. We'll then transition into Spring integration, talk about messaging use cases and how Spring integration provides a domain-specific language for messaging within your Spring application. Then we'll transition into AMQP. We'll talk a bit about why AMQP and AMQP Architecture. And finally, we'll end up with RabbitMQ and talk about RabbitMQ, which is an AMQP broker, and demonstrate some of its architecture. So I will have code that we follow through that I'll demo at the end of each of these. So we'll have some real-life example after the Spring integration talk. We'll have everything running on a single JVM, and then we'll distribute some of the components within our Spring integration flow after the AMQP session or talk, and then finally we'll show some of the enterprise capabilities like high availability of the RabbitMQ broker. So some trends within modern applications. First and foremost, applications today are being written with frameworks like Spring, and Spring integration is a module within the Spring community, within the Spring framework, that developers can use to implement messaging within their applications. So frameworks themselves are embedded within your application and actually distributed with. So much different than how we have deployed applications that use messaging in the past, which is very server-oriented. Frameworks, of course, focus on developer productivity and innovation, and de-emphasize, the importance of, a particular broker or application infrastructure underneath. We have an explosion of new devices, so that this greatly, expands the number of concurrent users. So we need to, use messaging and asynchronous architectures to reach larger, wider audiences on the internet. Also, we need to release applications early and often, as oftentimes these applications are bringing value, to our customers and to our partners. Applications are increasingly data intensive, so as we distribute applications within the cloud, how do we make data ubiquitously available? Certainly messaging is one route, and that is more of a just-in-time delivery of data within these distributed applications, as you'll see today. Finally, applications are being distributed within both virtual and cloud infrastructure, so that you might have certain components of your application running in the public cloud and others running in the private cloud, and we'll actually show when we get to the RabbitMQ and architecture for doing so. So modern applications need modern messaging. As we move to the cloud, traditional approaches to messaging really imply predictable static interaction between well-known endpoints. Modern approaches to messaging embrace the unpredictable, dynamic and transient nature of the web, and this, creates new burden, new, responsibility upon our messaging tier. We'll be talking about, obviously, the frameworks and the runtimes that are targeted for that new generation of applications that use messaging within them. Synchronous architecture, from the legacy days is often brittle, right? So many of us have experienced this type of architecture where I have a synchronous transaction that is running from client all the way through multiple tiers and back, right? And if any component becomes unavailable within that synchronous flow, all the in-flight messages, will be affected, regardless of what component they're currently in. And, again, since state is maintained across all of these components, this system can be difficult and complex to reset. Asynchronous architecture is much more popular within the web. So, I place an order. I have application components that are listening for orders, from a shared broker cloud. So this isn't point-to-point messaging. It's more publish-subscribe, and different components can fulfill different parts of the order. Obviously, I can check the status of my order while this is going on, and these are all asynchronous, straight-through processing type of components. In this case, if we lose any individual component, if an individual component is lost, only the in-flight messages within that component must be redelivered. Furthermore, since we have modularized our application and using messaging to communicate between them, all state is maintained within the messages that are being passed, so that it can be very easy, to quickly re-provision components that have failed. So how is messaging being used within modern applications today? Eventing, I need to know when to do something, so the concept of an event-driven consumer that kind of wakes up when a message arrives on its inbound channel. Fragmentation, where maybe I want to break up this order into individual order items and give just those individual items out to different components for processing. Routing, and we'll be showing all of this within our example here in a moment. Control who gets which message without changing sender or receiver. Batch. So, batch is still a very big component of modern application architectures, and really what it gets down to is the ability for producers and consumers to run at independent times. So, messaging and message brokers do provide us with that store and forward capability that allows for near-time, batch application runs. Publishing. I simply have an event, and I want to tell everyone about this event, regardless if anyone is listening or not. And finally, modularity. As we discussed before, when we begin to deploy our applications within the cloud, messaging, can really help us modularize our application, and that modularization also drives our ability to scale that application. I'll be using a cafe example, which is very similar to a Starbucks. And the thing that I like to say is, to serve the next customer, it's much easier to hire an additional barista than it is to build a whole new Starbucks store. Finally, versioning within a distributed system is also enabled, through routing and other, patterns that you see here. So we'll talk about Spring integration, which is the framework within Spring. At its core, it's an embedded message bus that runs within any Spring application context. All components within a flow are Spring-managed objects. So it's basically an extension of the common Spring API that you're likely familiar with. And very easy to incrementally adopt messaging into your Spring application. So if it's a web application, you might start off simply by distributing the front end from the back end by introducing a channel, a Spring integration channel between your front controller and your application controller. Spring integration is also an application integration framework. It connects to other systems via adapters. We'll be focusing on the AMQP adapter today, Adapters come in two flavors, unidirectional, so either inbound or outbound, or bidirectional in the case of a messaging gateway. We'll be showing both within our example. So just to give you a quick idea of Spring integration and its domain-specific language, we have common enterprise integration patterns here from Gregor Hope, and that really is the domain-specific language for messaging that Spring integration provides to your Spring application. So as you see here, I have a barista bean, which is a managed bean within Spring, and I am essentially invoking a method on that bean called prepare hot drink when I receive a message on the hot drinks channel. The result of that method is placed on an output channel called prepared drinks. So very easy to introduce event-driven consumers, using the proxy capability of the Spring container. Fragmentation, again, Spring integration supports a wide range of enterprise integration patterns, including splitter aggregator that we'll be focusing on today. So this just shows, the ability to split an order into individual items, and then to route those items to different channels based on information in their payload. So in this case, a Boolean called iced. So if true, route to a cold drinks channel. If false, route to a hot drinks channel. Batch, as we talked about, is a good example of that as aggregator, where we are basically placing correlation IDs on the outbound messages in our gateway, and as we receive responses back from the baristas, we aggregate the individual order, and we have a completion strategy implemented within our waiter Java class, as you see here, that handles the aggregation of all of those drinks once we've received them all for delivery back to the customer. Again, publish, we're going to be showing, publishing within an AMQP broker on an exchange, but it's important to note that even if you don't distribute, you can use Spring integration for eventing within the Spring container itself. So the Spring container does, provide, is an eventing container, and Spring integration makes it very easy for you to publish within that container as well. Modularity, again, it's a matter of configuration, not code, to basically take an application that is fully deployed on a single JVM and distribute across multiple JVMs. So in this way, Spring integration really doesn't force you to finalize your decisions around deployment before testing begins. Individual modules, can be version deployed and scaled independently at any time, through configuration and not code. So that's what we're going to focus on here with our Spring Integration Cafe demo. And this is a very simple example, but one that we're all pretty familiar with. We have a publisher that represents a customer, publishing orders on a messaging gateway called Cafe that places orders on a channel, which is then split into individual order items or drinks that are then routed to either cold drink or hot drink channels based on, the Boolean within their payload. We, of course, have the aggregator then that is, aggregating those messages on return and publishing the delivery of those completed orders on an outbound channel. In this case, that outbound channel is simply standard out. So with that, I'll show you the Spring integration XML configuration that implements that simple flow that we saw there in picture. So here you can see the individual gateway for the Cafe. It's placing orders onto an orders channel, which is then being split. The individual drinks are being routed based on their payload, the Boolean within their payload, to either the cold drinks or the hot drinks channel. And then we have event-driven consumers, service activators that basically wake up when new drink orders are placed and either prepare the cold drink or the hot drink and reply on the same channel, prepared drinks. We then have an aggregator that's listening on that channel that uses the correlation ID on the messages. And again, we don't have to do any of that, right? That's all handled by Spring Integration for us, the correlation. And when it has received all of the message in response, then it's going to invoke the waiter Spring Bean and generate a delivery, which is then being sent to standard out, as you see here. So just to give you an idea, we'll execute that all within a single JVM. So I've got a simple application that basically runs all within my local JVM, and basically all I'm doing is bootstrapping, with the XML file that you just saw there, and placing 100 orders on the cafe gateway. You can see the orders coming through in the console below. Okay, so with that, that shows basically our Spring integration. It shows the full Spring integration flow running within a JVM. But what happens when I want to begin to distribute it? Channels are an abstraction within Spring integration, so I can use multiple methods to distribute my applications: JMS, HTTP, either web services or REST, or AMQP. So we're going to be focusing on AMQP today. And we'll start off with kind of an introduction to what AMQP is. It's a little bit different than JMS in that it is a wire-based protocol, not an API. So that's first and foremost very important. Think SMTP, but reliable. So it is an open standard protocol based on TCP that is aimed at providing asynchronous, reliable communications over the web. So again, AMQP is a protocol, not an API. That means it has wide, client support. Java is just one client. .NET and Ruby, Python, Perl, any number of clients are implemented, and of course each one provides their own API around that messaging. So this gives you broker independence, as what's being spoken is a standard API to the broker, or I'm sorry, a standard protocol to the broker. So you can switch brokers without changing your application. So it is. So the AMQP also does does also define a set of messaging capabilities for the broker that is called the AMQ model. RabbitMQ is one example that we'll be focusing on today. That implements that AMQ model. Messaging is very fast. You can specify persistence as a quality of service on the message itself, so you don't have to declare that at the queue level. This means that, for a lot of the eventing that we do within modern applications, we likely don't need to persist those messages. This allows for much higher throughput. Of course, if we do need persistence and message guarantees, certainly we get that with both AMQP and the brokers like Rabbit. AMQP is highly secure. So first and foremost, AMQP over SSL is supported, since this is a wire level protocol that runs over TCP. I've even gotten it to run over an SSH tunnel. So very easy, to secure communication in transit. Also, to connect to a broker, there's two levels of security. The first is a virtual host, very similar to a web server, that has, individual IDs and permissions for those IDs defined on it. There is 3 levels of permissions within AMQP security. First is configuration, which allows you to define things like exchanges and queues and bindings. The second is publish, and the third is consume. The AMQ model is really designed for brokers to be able to scale horizontally. So dozens of clustered brokers are very common, and this allows for very high message rates. And of course, I can scale out, adding additional brokers to support more publishers or more consumers, and of course scale back when that load goes away. A little bit about AMQP architecture. So we do support the concept of direct messaging, but it's important to note how it's different from JMS. Instead of publishing directly to a queue, we always, in AMQP, publish to an exchange. The broker then handles the routing of messages from an exchange to a queue. In the case of a direct exchange, which is our most simplest form here, the routing key that is used when we publish the message is the same as the name of the queue. So I have a direct exchange that has a new order queue defined on it that is bound to that exchange with a binding that uses a routing key equal to its queue name. When I publish messages, I publish them to the exchange using that routing key, and that will direct messages directly to that queue. So as a publisher, I choose which exchange I want to publish to, and then the broker handles routing within that exchange, to different queues, and ultimately to consumers. So I can have multiple consumers listening on a queue, and AMQP will support, simple round robining between them. So I have messages that are delivered, and so they're published to the exchange and delivered through the broker to those queues, which then my consumers consume off of. A different exchange type, so that was direct exchange. This is a fan-out exchange. Again, very simple. I have a message that I'm publishing to a fan-out exchange, and any queue that is bound to that exchange will get all messages that are published on the exchange. So I might have multiple consumers across those queues, and they all get all of the messages, except in this case for the 2 consumers that are consuming messages of this queue. They would get round robined. The final exchange type that we'll talk about is a topic exchange. And again, when I publish a message, I publish it with a routing key, so I can have multiple queues that are defined, and they're bound to a topic exchange with a routing key pattern. So all drinks is bound using drink.star, whereas cold drinks is bound to the exchange with the routing key pattern of drink.cold and drink.hot. So if I have a message that is published with a routing key of drink.hot, that is going to be routed by this exchange to both the all drinks and the hot drinks queue. So that star is a wild card, essentially, in the all drinks binding. Drink.cold, again, delivered to both the cold drinks and the all drinks queue, and then finally, drink.warm is only delivered to the all drinks queue. So with that, we're going to show how we distribute our simple Spring Integration Cafe example using AMQP. So the first thing that I'll do is actually show you the how I've distributed. So I basically expanded the Spring Integration Cafe example, again through configuration, not code, to allow for transformation of orders to JSON. All communication over TCP is byte-based, so we're using JSON strings. So we're transforming the orders that are placed on the inbound channel and placing them as JSON orders onto using an outbound AMQP adapter for the Cafe orders exchange. Again, our broker is handling routing of those orders to the new orders queue, which then we have an inbound channel adapter listening on for the Cafe itself. And it's the Cafe that basically takes those inbound orders, splits them, and routes them to the baristas. The baristas themselves are also distributed. So I'm using a messaging gateway here, which is bidirectional. And in this case, we are using temporary reply to queues that are specified in the message header as the cold drink orders are actually published out to the baristas. So the baristas receive the message and they know which queue to place the prepared drinks back on. Finally, as those prepared drinks are delivered, we're transforming them, aggregating them, and then transforming the deliveries for publish back to a Cafe Deliveries Exchange using an outbound AMQP adapter, as you see here. Our baristas are running on separate JVMs as well, so that's 4 JVMs total. We have the storefront, the actual cafe, and then the 2 baristas. So these JVMs are very simple. They're listening on an inbound, messaging gateway for messages that are sent. Again, those messages are each going to contain, a reply to queue to place their reply message on. So they go ahead and transform for JSON to object. They invoke, the method on the barista Spring Bean, and then transform back to JSON, the prepared drink, and place that on the appropriate queue. So we'll take a quick look at how that is defined within, our Spring integration. So the important thing, as we look here, this is the cafe. So this is the storefront, I should say, for the cafe, where we take new orders, place them on an outbound AMQP channel adapter, as you see here, specifically, on the Cafe Orders Exchange. The nice part about Spring integration is that it provides, full support for Spring AMQP, which in turn allows me to define those exchanges and queues right within my Spring application context. So here you can see I'm defining new orders queue and the all orders queue. Down here is where I'm defining those queues, and then I'm binding those to the Cafe Orders Exchange using the following patterns. So I can do all of that, within my Spring application context. Here's the operations, or the cafe itself, that takes those orders and splits them, routes them. So you can see, the routing to the baristas here. We're using, the messaging gateways as we talked about before, and we're using different routing keys, when we publish these messages. So that the broker will deliver them appropriately. When we get things back, we basically aggregate the response and place the deliveries on an outbound adapter, which is publishing to the Cafe Deliveries Exchange. Quick look at one of the baristas. Just shows that the barista is the inbound side of that messaging gateway. So we have an inbound gateway that is basically listening on the cold drinks queue, and that queue is defined down here, again within our Spring application context, and bound to the cafe drinks exchange using the following routing key pattern. Once I get a message, I'm transforming it. I'm basically invoking the prepare cold drink method on the barista bean, the Spring managed bean, and then transforming the response back to JSON. Note that I don't have to specify anything related to the reply. That's all handled by the inbound gateway. So it knows the reply to queue, then to place that JSON prepared drink on. All of these are using the same AMQP config. So basically this is where I'm connecting to a RabbitMQ instance. It's running on my local host, with a username and password. So the virtual host is just the slash virtual host, the base or the root virtual host in this case. All right, so in this case, I can now take my Cafe demo app, and instead of invoking one that bootstraps with the Cafe demo XML, I can bootstrap with the Cafe demo AMQP XML, which is the configuration we just looked at, which is going to, again, place those orders on the Cafe orders exchange. So I can go ahead and run this. And if I flip over to the management console for my RabbitMQ, I can see that basically I published 50 orders onto the Cafe the Cafe orders exchange. Those orders were routed based on the routing rules here to both the all orders and new orders queue, also to a third queue that I'll talk about in the next segment, based on the routing key patterns that you see here. So I do have the 50 orders here. If I wanted to take a peek at those, I can use my management console to do that. This is real handy for debugging. So I can say requeue after I take a peek. So I'm going to take a peek at one message, and we can see what the message looks like here. It's basically a JSON string that represents the order item or the drink that the drink order. It's not an order item. This is actually a multi-item order. That is published by the customer to the Cafe storefront. So nothing has processed those orders yet, and this is because I haven't started up the other components of my application. So I'll go back into STS, and first I'll start up the two baristas. So again, each of these is going to run on separate JVMs. And once I start those up, I should see those queues are now defined. So I see, first and foremost, the Cafe drinks exchange, with the cold drinks and the hot drinks queues, bound with the appropriate routing keys. And again, that was all from the Spring application configuration that you saw. So those queues and that exchange did not exist on the broker before I started the application up. All right, so we still aren't processing anything, and that happens when we start up our Cafe. So we'll go ahead and start that up. And this is what is going to then take those 50 orders and begin processing them. So I can see, the standard out, that's showing up here. I can also follow this within my RabbitMQ console. So you can see the temporary reply to queues that are being generated both to the cold drink and the hot drink baristas. And I can see, the deliveries being processed, by the outbound gateway. Notice that my new orders queue is down to 0. So I took those 50 messages and, and processing them, essentially, as you're watching here. All right, so that was how to take, our Spring Integration Cafe example that ran on a single JVM and distributed across multiple JVMs through the use of simple Spring Integration configuration. So, I'm changing the abstract channel definition from being a Java channel to being an AMQP channel, essentially. Now we'll talk a little bit about RabbitMQ. And, what is important about RabbitMQ from a message-oriented middleware perspective? First of all, it's very lightweight. The broker is meant to be, started up very quickly in response to load and scaled out horizontally, in response to load. So this is very different than middleware, legacy middleware that's out there today. Also, from a licensing perspective, if you want to get support from VMware, we license based on average usage, meaning that, if you have a peak period that runs for 2 weeks or so, that gets averaged out over the whole year, that the licensing that you pay is based on average usage, not peak. RabbitMQ, again, is very tight. It's about 7,000 lines of Erlang code. It starts up in milliseconds. So, from this perspective, it can be spun up in response to demand in real time. And it is unlike a lot of its, a lot of the other alternatives in that respect. It is the leader, within the AMQP space, and has a great community, just like the Spring community. Many GitHub repositories that are out there. I've got one where all of this code is out there. I've also contributed much of this code back to the Spring integration samples, which is just another repository out on GitHub that you can go check out. RabbitMQ has a large number of enterprise users, such as this Tier 1 telco that's reporting 6 nines availability. Basically, has multiple Rabbit instances deployed in multiple data centers that have been up for well over a year without any downtime. It has enterprise features that you come to expect from other broker implementations, such as clustering. So in this case, the publishers publish to an exchange that is shared across all of the brokers in the cluster. So as brokers join the cluster, they get all those exchange definitions. And any publisher connected to any broker can publish to any exchange. Likewise, on the consumer side, any consumer can consume from any queue, regardless if it's on the individual broker that it's connected to. So queues do live on a single broker within the cluster, but we share their definitions across all brokers in the cluster. So I can consume from any queue within the cluster. So as we see here, our first consumer is connected to broker 2, but consuming messages off of Q1 on broker 1. I again can post messages to an exchange that routes to a queue that isn't on the broker I'm on, as a different example. And finally, as a consumer, I can consume messages from multiple queues that may or may not all be on the broker that I'm connected to. RabbitMQ also provides fault tolerance, so it does this with the concept of mirrored queues. So as I said, a queue lives on a specific broker. I can mirror that queue on all other brokers in the cluster or on a subset of brokers in the cluster. So I have a very simple cluster here with two instances, and I've got my cold drinks queue mastered on broker 1 and mirrored on broker 2. Conversely, I have hot drinks mastered on broker 2 and mirrored on broker 1. If I were to lose broker 1, basically the mastering of the cold drinks queue gets transferred to broker 2. And then if I were to bring broker 1 back into the cluster, those queues come back as slaves to the current masters. Again, our mission with RabbitMQ is very, akin to our mission around Spring, and that is really to provide you with public to private cloud portability. So, from that perspective, we want RabbitMQ to just be there, regardless of what deployment destination of choice you have. And even if you don't choose to use RabbitMQ in every one of these different deployment destinations, because you're using AMQP, that choice of AMQP provider is yours. So, if you have a private cloud with a different AMQP provider, certainly you can deploy it there. And if you want to publish it to a public cloud that has RabbitMQ, again, no changes to code are necessary, or to configuration, for that matter, within Spring. So finally, we'll kind of wrap up with a brief overview of, a deployment of the Spring Integration Cafe using RabbitMQ in a hybrid cloud setting. So here I have one instance of an AMQP broker that is kind of acting as a proxy for orders that are placed. So, I could be potentially having this out in my DMZ or in a public cloud, and I might be terminating SSL here, in some of those scenarios. So I've got, an application that, lives in the cloud that's generating orders against that queue, but none of my back-end processing is actually hooked up to that broker. So RabbitMQ does provide very robust broker-to-broker messaging for distributed messaging patterns like this. So in this case, I'm going to be showing Shovel, which is one of the plugins. There's another called Federation that you can check out. But essentially, what we're doing is we're taking messages that are published or routed to a specific queue on this broker and publishing them to an exchange on our cluster. That cluster could be running inside of our intranet or inside of our private cloud. And again, it's using AMQP for that communication, which is, could be routed, again, over SSL or, or even SSH tunnel, however you want to do that. And then on the cluster itself, I've got my other deployment units, the Cafe Ops, the two baristas. They all have redundant connections to both of the brokers in this cluster. So with that, I'll kind of show the broker configuration that I'm using for RabbitMQ. It's pretty easy to read. So I am defining a shovel on my host broker. So I've got one broker running on my host that basically represents that proxy that is shoveling orders that are published to the order shovel queue over to a set of brokers that are running in virtual machines on my laptop here. Those brokers will be clustered. I'll show you how we do that. And essentially, you can see that I'm reading messages, from the order shovel queue, and I'm delivering them to the Cafe Orders Exchange on those destination brokers. This is a failover connection, so if I were to lose one of these brokers, it would route to the other one. It basically uses a round robin scheme under normal conditions. Conversely, I've got a shovel defined on the clustered side, which is mainly oriented at taking deliveries that are published by my local components, by the cafe ops component in particular, and shoveling them back over to my proxy for delivery to clients in the public cloud. So again, I can go bi-directional. So in this case, I've got this shovel defined on both of my clustered brokers, and I'm shoveling to the broker on my host as the destination, reading from the delivery shovel on my clustered side and publishing on the Cafe Deliveries Exchange on my host broker side. So the way that all looks within RabbitMQ, I can look at the shovel, so I can see I've got an order shovel running here that is currently up and running. It's shoveling orders over to this host, which is the IP address for my first VM. So let me show that VM. All right, so if I go into the queues, I can see that the 50 orders that I delivered already have been shoveled. They have not been processed, so that's because I haven't started up any of the back-end components yet. These queues are, these two brokers are not currently clustered, so you can see that my second virtual machine does not have those orders. To cluster them is very easy, and I'm going to take down and start up the cluster, so note how fast, or the server, so note how fast that occurs. So I'm going to issue a RabbitMQ CTL stop app. That basically stops our running broker on the second broker. And then I'll issue a reset. And then I'm going to cluster this broker with the broker on Rabbit Ubuntu 1. So that's basically how easy it is to cluster. Now I can issue a start on this broker, and if I flip over, I see that here are the 50 orders that were previously on the other host. So I know that I'm sharing the queue now. Also, I can verify that by going into the Overview tab and see that I see both nodes participating in the cluster as disk nodes. So that's important for durability of the exchange and queue and binding definitions that are there. All right, so now I'm going to show my configuration on the Spring integration side that allows me to basically consume messages. So just to give you a quick idea of what that looks like, you've already seen the configuration for the AMQP. So I'm going to open the same configuration files for AMQP, which are just in a different folder, that I bootstrap from. And the important thing that we'll look at here is the operations. So we can see. Well, first we'll take a look at the RabbitMQ config here. So you can see in our template we're actually specifying the address of both of our brokers. And we're also defining a policy for queue definition called HA-args that can be applied to any queue that we define in the cluster. And then if I go back to operations, we can see that I'm defining queues right within my Spring application context as before. So here's one of those queues, and I'm just giving it the HA-args policy as a queue argument on the queue declare. So this will declare all those queues as highly available or mirrored. Also, for communication with the baristas, I am using different templates that specify different reply to queues. So these are well-known reply to queues. We're not using temporary ones as we did in the previous example. Those are specified at the template level. So we've got one for cold drink replies, one for hot drink replies. The reason we do this is so that if we have a broker failure event, those well-known queues are failed over as well. So with that, I'll go ahead and start up my baristas first. Since I don't need to publish any more orders, they're already out there from the shovel. I'm just going to basically change the file that the Spring application context that I'm bootstrapping with. So first, I'll start up the baristas. And note that I have those queues now defined in my cluster. So you see the cold drinks and the hot drinks queues, and they're defined as highly available. If I refresh this, I should see which node they're currently mastered on. So you see, they're currently mastered on Rabbit at Ubuntu 1, and again, that shows over here as well. So again, we aren't processing any of these orders yet. So what we'll do is switch over and basically start up our operations, which is going to connect to that cluster and begin processing the orders that have been placed out there. So again, I can watch this all occur within my RabbitMQ console as before. I can see the messages going across. I can see that they're all currently mastered on Rabbit at Ubuntu 1. And then, I can basically go here and issue, a stop app or a stop to stop this broker. And when I do that, I should see all of the queues fail over to Rabbit at Ubuntu 2, as you see here. And the messaging from Spring Integration will pick up in a moment, and we'll continue to see the deliveries there. All right, so with that, that's what I had to present today. I'm going to stop and answer any questions from the audience. Okay, so first question, if AMQP is a wire level protocol, what is the API to send a message? So there is the API is basically an AMQP specific API. Some allow you to use JMS API. Some brokers do not. So the question was, is JMS, can I speak JMS to an AMQP broker? The answer is yes. We don't implement that within our broker today, but certainly you can bridge from JMS to AMQP using Spring Integration. So that's our strategy. We are looking at implementing JMS API within our Java client for RabbitMQ as well. I'm assessing which platform cloud to use for a startup, Spring versus .NET Azure. Can you, please point out the most important bullet points that make this approach better? So, basically we want to allow for you to choose which cloud you want to publish to. So certainly Spring Integration is available on the .NET side as well, so for you .NET developers. And, RabbitMQ and AMQP both fully support .NET clients. The RabbitMQ client for .NET uses the WCF. So basically, a lot of solid .NET support. If you are developing Java applications, then you have multiple clouds to choose from, as well as if you're developing .NET. So Iron Foundry is one example of a .NET cloud that is not Azure. There are multiple, Java clouds that are out there, including, Cloud Foundry, which is the one that is backed by VMware. How could we elastically scale RabbitMQ on the cloud? So again, as we get more consumers, we might, with the transient nature of the web, we might temporarily create new queues, right, just for the duration of that consumer session. And essentially, as we create more queues, we're taking up space on the broker itself. So as we get more consumers, we can kind of scale out with additional brokers, and new queues then can get easily created on new brokers. Assuming they're all clustered, everybody still has visibility to everybody else, both from a consuming and a publishing point of view. What are your preferred alternatives to RabbitMQ that you would recommend, low cost or open source? So RabbitMQ is open source. That's very important. You can optionally choose to get support from VMware, so that's a good thing, right? You can start off using it, and if your application takes off and you need support, you can get that from VMware. So that's really our value proposition around RabbitMQ. But certainly, the code, which is Erlang, is open sourced, and you can use it within your Spring applications freely today before choosing to go with a support option. How would I characterize the essential differences between mirroring and high availability? Well, they're really complementary, right? So mirrored queues, are basically only implemented within highly available clusters. So I can easily define, the buddy nodes that I want to mirror that queue on, and I can have that be every node in the cluster or a subset of those nodes. So, basically clustering does not automatically mean mirroring, right? So that's an important distinction to understand. So I can choose certain queues that need to be mirrored. Maybe others don't, right? Especially if they're more transient in nature, or if they're just representing event-based communication rather than guaranteed messaging. So again, that flexibility allows you to control easier the need to horizontally scale that broker. The more guaranteed messaging you do, the more stateful those client connections become. So you need to scale out faster under load, right? The more stateless messaging that you do, the easier it is to scale to a large number without having to add a lot of additional brokers, right? How can we try RabbitMQ? It's, again, free to download right off of the RabbitMQ.com site. Please visit it. There's great cookbooks out there. Also, if you're Spring fans, check out the Spring AMQP and Spring integration projects for more details on our AMQP support. Start with Spring AMQP, and then most of what you saw here today is basically what we have to offer within Spring Integration AMQP. The demo code is available. That is out on my GitHub that you see here on the slide. And I think that's about it. For those who had questions that I didn't get to, I will certainly try to follow up offline, or feel free to post them within our forums. You have my Twitter and my email here as well, so feel free to communicate with with me directly on any questions that you might have. Thank you very much.